what we're going to be working on this week is dealing with how all of that stuff about seeing rates is useful for us. How we can use information about how we know rates behave and how that relates to graphs in order to help us solve some problems that with just algebra would be a little bit tricky. So the process that we're going to talk about this whole week involves what's called optimization, or finding like the best value. So best is kind of depends on what you're trying to do. So it's called optimization in general. But critical values are those kinds of points that we were just discussing where it says, oh, did I start the recording? Yeah, I did. Okay. Sorry. Where the sorts of values where, like, well, is the function increasing or decreasing? I don't know. This is kind of the point where it turns around. So it's a point like that where there's something unusual happening, and they're identifiable most often by their derivatives, looking at a function rule, because thinking about derivative values of points like that where they're like, it's turning around and going some other direction, or maybe it's just twisting, maybe it's stopping, curving upward, and then it begins to curve downward, meaning you're at the steepest point in a graph. Something like that might be what you're looking for. Trying to find those sorts of things by determining, like thinking about algebra, what sort of x value makes the y value biggest isn't something you can like take an equation and set it equal to biggest and solve. You can't do that. But if you know that at a biggest value, that maybe your derivative is going to be equal to 0. Equal to 0 is a sort of equation that we know how to solve. Equal to biggest possible is not. So using what we know about derivatives, we can locate these analytically, and so we can get more precise values than just like eyeballing estimates. But we do have technology, so we can get some estimates to whatever degree of accuracy we want from those as well. But a critical value is a point that's one of these types. It's a value where the function, a critical value of f, would be a value where f of x exists. So I have an output, so I have to be at a spot in the domain where the function value exists. And I have either the derivative equal to 0, which would indicate one of those sort of flat spots, which are usually of interest for some reason or another. Sometimes they're what we're looking for, sometimes not. But those kind of turnaround spots, or just flat spots in general, you can locate by determining where the derivative is 0, or sometimes we have slightly less neat functions, not all nice, smooth, curved functions, but sometimes we have a derivative that doesn't exist that could indicate a highest point or a lowest point or a point of interest because we come to a peak or a corner, and that's maybe something of interest. That would be a spot where a derivative doesn't exist. And locating where a given function rule, we can set a function rule equal to 0 and determine where is the derivative equal to 0, or determining where it doesn't exist, things like when is the denominator 0, or when would this become a square root of a negative or a log of a negative or something like that. Those are things that we can solve for also, sorts of things that you did a lot in probably algebra classes, determine the domain, thinking about when something would be undefined. Those sorts of values we can locate using sort of algebra skills, solving, as opposed to just when is this the biggest I can imagine. It's kind of a vague question. So the thing is, if I do have f prime at some value c, f prime of some number equal to 0, it's not necessarily exactly what I'm looking for. There's a few options of what it could be. But what I do know, if I know that I have a derivative value of 0, I know that that indicates a rate of change of 0, or essentially 0 in the moment, meaning I've got kind of a pause of some sort. So I was going up, and then I stopped going up. Now what happens next determines what sort of point this might be, whether it's of interest or not. So it could be stopping from increasing, could be stopping from decreasing. It could have just been constant all along if it's a very boring derivative function. But there's a few different combinations of what could be happening, and it's not just dependent on the value at a particular point. We need to look around that point, because we're talking about rates of change. We have to look about, well, what changed into what? I know that I have a rate of 0 essentially 0 right in one moment, but was it coming to a halt and then just stays there? Was it increasing up to a point and then decreasing? Was it increasing up to a point and then continuing to increase? What else is going on either side of that critical value, that point x equals c? So there's a few different options. So I just want to demonstrate kind of what could be going on, the descriptions I was saying aloud just now. But I could have what's called a local maximum. I hope that's a term that sounds familiar from a previous class. A local maximum is like at the top of the hill, something that's higher than the points around it. Which, if I have a local maximum, that means that as x, or whatever my independent variable is, increases, my y value increases and then hits my maximum and then decreases. So I have a rate of change that's positive, then 0, then negative. My function's increasing, then kind of hits a pause, and then decreases. The y values of the original function f, which would indicate that the rate function would have to be, well, it's 0 at c, but it would have to be positive before that, and then hit 0, and then be negative afterward. Or in other words, if I know what my function rule is, I can figure out where the rate of change is equal to 0 analytically using algebra and taking derivatives and stuff. But if I was looking at my rate function, it would have to be something that's positive of some sort, then hits 0, and then is negative. So maybe, something like positive, but goes to 0, and then negative after that. In order for the critical value, this point C, to have been what's called a local maximum. So and we can tell that from sometimes looking at functions, just the style of functions. Sometimes it's very easy to tell, oh, well, this hit 0, but before it was positive, then it turned negative. So it's something simple like 5 minus 3x, something like that. Yep. Once you hit 0, that means x is big enough. It's going to continue to be negative after that. So this must be a maximum that we hit, and then the function is decreasing beyond that. So if I have a rate function that's decreasing throughout, what do I know about the second derivative? My rate function is decreasing. So f is something that increases, pauses, decreases, meaning my rate function goes from positive to 0 to negative. Positive rate, 0 rate, negative rate. So meaning the rate function graph could maybe look something like this. What's the rate of this graph look like? The rate of this blue line that I sketched? Well, it's decreasing all along, right? So going from positive to 0 to negative in terms of y values, if I think of, well, what's going on with this graph? Well, this looks like a line with a negative slope. So its rate of change is just negative all the time. Or if I were graphing the second derivative, to match up with this, if this is actually a line here, then if I were graphing the second derivative, it would be a constant negative value. So maybe this is a line like y equals 5 minus 3x. Well, its derivative would be negative 3 all along. So whatever this might look like, but this is negative throughout. This is positive, 0, negative slopes or steepnesses on this graph, increasing, pausing, decreasing y values. Then I know that the rate of change of that would be a decreasing function, or just thinking about this, oh, this is concave down all along, or this is curved down all along. That means I've got a negative second derivative all along, all throughout that domain. So again, just kind of matching up graphs of first and second derivatives, but their properties can tell us something about what's going on with our function also. So if f prime of x is 0, I could also have a local minimum, kind of the opposite of this. The derivative equaling 0 doesn't mean I have to be at the top of a hill. It could mean I'm at the bottom of a hill. Or it could mean some other things also. But at the bottom of a hill, I would have some changes from what happened above. In order for us to be at a local minimum, that would mean that, well, look at the line above. take a minute, see if you can figure out what properties in terms of increasing, decreasing, positive, and negative the rate function and the second derivative, the rate of change of the rate of change of function f would have in this local minimum situation. So again, just instead of just imagining the shape, you can also think of as the x increases, what happens. So you can see the changes. So again, our local maximum, in order for us to be going up and over the top of the hill, we would have had to have had a positive rate that turns closer to 0, turns into 0, into the negatives, and so forth. So that would be a rate of 0 at the top with a positive rate to the left and a negative rate to the right. So we've got to have the reverse here to be going downward, reach a bottom, and then go back up. We have to have a negative rate that then pauses or becomes essentially 0 and then turns positive afterward. Or since f is decreasing, then pauses, and then increases, that means its rate function is negative and then essentially 0 and then positive. Which, if I want to know how my rate of change is changing, going from a negative to a 0 to a positive, negative to 0 to positive, and it doesn't necessarily have to be a straight line sort of thing, but just anything that negative, 0, positive, that's an increasing sequence of values. So this first derivative is increasing, which means its derivative would be positive all along. Or if I wanted to, sketch something, whatever I might pick, maybe it's a constant positive value, maybe it's a varying positive value. I tried to draw this a little bit curved here. But the second derivative would be positive here. So there's different ways analytically or using the formulas and doing algebra and calculus that you can find this as opposed to just looking at graphs. But if you're looking for something that's a local minimum, then you could say, well, I know that the first derivative would have to be 0. And, well, if I knew that I had either a pattern of positive, 0, negative first derivatives around that, or I knew that I had a negative second derivative, then that would tell me I'm at a maximum. Or if I was looking for a minimum of a graph, a minimum position, a low spot, then I could determine, okay, well, I'm looking for a spot where my first derivative is 0, potentially. If it's a smooth bottom of a curve like that. Where's my derivative equal to 0? And does it go from a negative rate to a 0 rate to a positive rate? Or, in other words, is the second derivative always positive in that region? Or is it something else? So it's not always the easiest to determine, but there are a lot of analytical things we can do. We're going to look at a chart in just a minute. The only thing is that if you know that the derivative at a specific point is 0, you don't necessarily have one of these two organizations of what's going on with the first derivative, because there's two options for what could happen on either side of the position where the derivative is 0. I can have the derivative equal to 0, and if it exists on both sides, I could have positive, 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 negative, negative, positive, negative, negative. There's 4 different things that could happen. This is only 2 of them. The other 2 combinations of positive and negative values of a first derivative on either side of a 0 first derivative, a flat spot, are not quite such useful things necessarily, but good to know that they exist. Because, for instance, a spot like this, even things like a y equals x cubed graph, this is a little bit fancier looking than that, but y equals x cubed graphs have a flat spot in the middle, right at the origin. And at that, if you take the derivative of y equals x cubed, you get 3x squared. The derivative is certainly 0 when x is 0, but that is not the top or bottom of a hill. That is just a flat spot, kind of like that. but how I could distinguish this analytically without having to do a graph, because this is, you can see it's a little fancier, curvier looking. It's not necessarily just as simple as, oh, well, I could just graph it and see what it looks like. Maybe it's a big mess, you're just staring at it. Well, if I know that the derivative is 0 at that spot, as long as I look at what's going on around it, so this graph is increasing and then pausing or flattening out. So it's kind of like I'm at a plateau climbing up a mountain, got to a ledge, stopped for a little bit, then we continue climbing. Notice that this is increasing and then just a pause and then increasing again. Not a change of direction, but just a pause or a rest stop or whatever. There's not an official name for that. I think this would be called a flat inflection. But just, it's not a change in direction, it's just a pause without a change in direction. Meaning the rate function would be positive to match that increasing f value, and then 0, and then positive again. So if I'm graphing the rate function, positive 0, then positive again, is not passing 0 and becoming negative. Like we needed a sign change in order to have that go around the corner and change directions. Positive, then 0, then positive again would be, let's see, if I'm graphing something that has positive y values, and then 0 y value, and then positive y values again, might have something like this. Which, if I were to try to describe the rate of change of this, the second derivative, like, all right, well, the rate of change of this is negative, and then essentially 0, and then positive. All right, well, what does that mean? Well, it just means it's different from what was going on before. So I've got a negative rate of change of this red rate of change function, and then 0, and then positive. So if I were graphing this second derivative, I have negative values, 0 values, positive values, something like, it doesn't have to be a constant increase there, but just something that goes like, so it's a different set of values. I have to go from negative through positive. But the point is, regardless, you don't necessarily have to graph these things, but just the pattern of derivative values. When I have an increasing function that pauses, then increases, or in other words, if I have a rate of change function that hits 0 but's positive on either side of that 0, that doesn't indicate that I've got a maximum or minimum. It indicates I've got one of these going uphill plateau sort of ledges. Climbing a mountain and I stop for a rest break. So could be the other direction as well. And you can maybe see what the pattern there would be. Excuse me, please. So in this one, you're like going back down, walking down the hill, you find a little rest up, and then go down again. So I've got a function that's decreasing, then pauses momentarily, or becomes a rate of change of essentially 0, and then decreases again. That would mean that my derivative function, the derivative of this, would have negative values, then 0, then negative again, as opposed to changing between negative and positive, like it does at a maximum or a minimum sort of point. So when our function decreases, pauses for a moment, and then decreases again, I don't have a maximum or a minimum, I just have one of these plateaus. And so it's not that this isn't a useful sort of spot. That might be nice to know where that happens. But just realize that not all places where the derivative is 0 are guaranteed to be magical, this is a highest point or a lowest point. They could be spots like these also, where it's just a flat spot in the middle of an uphill or a downhill, or in the middle of an increase or a decrease of the function's values. But you can determine that by looking at the pattern in the rate of change values, or seeing that, well, my second derivative was 0. A second derivative value of 0 doesn't tell you a heck of a lot. It tells you, potentially, that the graph is changing curvature. It could just be that the graph is extremely flat. Second derivatives of lines are 0, and they aren't doing anything fancy anywhere. Their second derivative is 0 all the time. So first derivative is a constant, second derivative would be the derivative of a constant, 0. So a second derivative of 0 just tells you something is flat or uncurved about the graph. It doesn't really tell you what's happening unless you look at the sequence of values as you go across. So In any case, this changing from negative to positive tells me the curvature is changing from curved down to curved up. And you can see that here. Oh, curved down changes to curved up. So that tells you, that's called an inflection where it does that. But it's not necessarily a high point or a low point because of that. So I want to take a look at this. So if you have a laptop with you, please feel free to use that. But what I'd like us to do is look at, and I'll pull these up in about 5 minutes or so, values for g of x, g prime of x, g double prime of x, or if you have a handheld calculator, you can use that too. But just calculating a bunch of values. Here's function g of x, a 4th degree polynomial. So just nice, smooth, curved thing, no weird corners, asymptotes, ends of the domain, or anything like that to worry about. But I want to take a look at what we can tell about the shape of the graph of this by combining information about what its y values are, what that does and doesn't tell us, what its rate of change values are, g prime of x, at each of these x values, and what the rate of change of that rate of change is, or how that rate is changing by looking at the second derivative's values at the same point. So I've got 0, a half, 1, 1 and a half, 2, and 3. So we can certainly look at a graph of this, but I'd like to take a look at just the numbers associated with this and see how we can match them up with what we can see in a graph, or how we could actually create a relatively reasonably accurate graph just from looking at these few numbers. Not a few overall, but your calculator does billions of computations or something. If we just do 1, 2, 3, 4, 5, 6, 18, we can get a good graph. So this involves a bit of number crunching, which we don't do a lot of that in here. Just as a forewarning, by the way, the topics we're going to be talking about for the next few weeks before your test all involve a bunch of problem solving. You have to set up a scenario and then find a final numerical answer to a somewhat complex problem. Not quite as much computation as involved here, but for your third exam and also your final exam because of that, if you want to use a calculator, you can have a calculator. It can't be your cell phone, but you can use a calculator of whatever sort you want. Nothing fancy needed, nothing particularly outlawed, just not a cell phone or computer. So just as a little bit of forewarning on that, because I'm not going to have you do something with this many computations, but there will be maybe some things where you don't want to have to divide by a decimal manually just because it takes a couple minutes. So in any case, if you do evaluate all of these, thinking about maybe even the sorts of things that we did on our quiz today, these are all relatively close to one another, x values, small x values between 0 and 3. And I can see as x increases, g of x starts at 3 and then decreases and increases and increases and increases. So if that's the only information you had about function g of x was just these y values, you'd have kind of an idea of what's going on. Say, oh, well, maybe g of x just kind of, let's see, if I only had this first column, I'd say, okay, it starts at 3 and then it goes down a little bit and then it goes up. So it ends up at, instead of being at 0, 3, maybe it goes all the way up to 3, 6. And it kind of hits a low spot in the middle. But if you look at some of the other columns here, we can get some more information about what's going on. Now, some of it will match that. It has to. In that, specifically, the rate of change around 0 is negative. So, okay, that indicates that going downhill. But if you look through this sequence of values, I've got a negative rate, and then 0, then positive, then 0, then positive. So thinking about what that indicates about a graph, just on its own, just the g prime values, I know that my graph should be going downhill until it hits this 0, and that hits a flat spot. And then I see positive, 0, and then, well, higher positive. So positive, 0, and then higher positive. So that tells me maybe my graph looks more like that between 0 and 6 because it's got this extra derivative of 0 in the middle that there's no way really to tell that just looking at the y values here, that there's this other flat spot or that plateau at x equals 2. Well, so maybe that's enough to kind of tell us the shape of this graph, but this second derivative, if I'm trying to graph the original function g, I can see that, well, the first half of this is all curved upward, and then I've got a downward curvature section, and then I've got upward again. So it's kind of converting from curved upward, inflecting or changing direction to curved downward, and then inflecting again to curve upward. Well, that's maybe kind of built into this, curved upward, and then switching around to curve downward, and then switching around to curve upward. So if we put all of that together, I'm going to plot some points kind of close to this. Let's see, 1, 2, 3. So we start at, let's see, we've got values from 3 to 6. So I'll just say 3, 6. All right, so we've got a point at 0, 3. At 1, 2, I'm just going to plot some of these so as to save ourselves some time. At 2, 3, and at 3, 6. And there are a couple others in there also, but kind of hard to see what's going on. So just how are these connected? You can tell more from these other columns here than from just looking at these y values and doing a lot more parts in between. So for instance, I know that around 0, I've got a negative slope. By the time I get to 0.5, my slope or my angle is 0. So I was going downhill toward this. It's not going directly towards this point. So I go down to 1 point something or another. Here, let me plot another point down there at 0.5. Maybe about here. there's a point. And at that point, that actually is a spot where my graph is flat. Now, it doesn't tell me that there's not like 3 other flat spots in between, because we only, I don't know what the scope of this function is. Like maybe I need to zoom in closer and there's lots of little wiggles back and forth. Well, but I kind of do, because it's just a 4th degree polynomial. There's not anything too crazy happening. But my graph, then I know it goes down. It actually hits a 0 slope, or a essentially constant rate of change at this 0.5 x value. And then it's increasing by the time I get to this point here. So I'm going downhill and then uphill, not as steeply uphill here as I was at the beginning, going downhill. And then increasing rate at 1, but then a less, let's see, so I have a positive rate at 1, and then it's becoming less until it flattens out to a rate of 0 again around 2. So in terms of my graph, it's kind of going straight across here. So I'm going uphill, but more and more slowly until I get to this spot here. And in fact, at x equals 1, my curvature changes. So I was going uphill. This was the steepest that I ever went uphill, because then it changed and started going uphill more slowly, or the curvature changed to go the other direction. And this, at x equals 2, this is actually the top of a hill, or this peak flat spot here. It wasn't just going up here. It's not going down. It's going up again afterward. But I can see that this second derivative is 0. So second derivative of 0, sometimes they're useful, sometimes they're not. In this case, this second derivative of 0 shows me where I was going from at x equals 1. I knew I was going uphill, but then I was going uphill more slowly, so it's that curvature change, or my second derivative was changing from positive to negative. At this one, I'm changing from negative to positive, which means at x equals 2, I'm changing again this way, or this is the flattest spot. Where the second derivative is 0, those are steepest or flattest spots in the graph, because those can be seen as maximums or minimums of the first derivative, maximum or minimums of the thing that they are the rate of change for. But kind of piecing this graph together, connecting the dots that we had, and the information about the curvature and the signs of the derivatives and relative sizes of the derivative, we can piece together what this function looks like. And if you were to graph this g of x function using GC, you'd see that between 0 and 3, it does look like that. It's not like, the y values, they don't go crazy and go all the way down to something else. But this is a low spot here at x equals 1/2. This is the center of this flat spot here at x equals 2. But just taking a look at all the patterns of the positives and the negatives when they change from positive to negative, when they hit 0, those sorts of things can tell you about the shapes of graphs. And what's important about the shapes of graphs is what those functions are actually representing relationships between. So those high and low points and flat spots will mean something in context. And that's what we're going to talk about Wednesday and Friday. We're going to piece together some functions and figure out when they're at their highest and lowest and how to determine what to do with that. All right, I will see you next time.